All right, for those who missed it, here's your lesson on trigonometric identities. So here we go. The assignment here is on the first slide. First of all, just understanding what identities are. An identity is something that is true, or it's a relationship that's true for all values of the variable. All values of the variable. A couple examples relating to some things that you should know. For example, a binomial squared, if you expand it properly, x plus 1 squared, for example, should be x squared plus 2x plus 1. This is always true. It's true for all values of x. Okay. On the other hand, if you do x plus 1 squared like incorrectly, or if it's just given to you as an equation like this, x plus 1 squared equals x squared plus 1, this is only true sometimes. Only true sometimes. It's an equation then. So you could be given this as an equation you could solve, all right? But it's only true for certain values, whereas the correct expansion of the binomial is true for all values of x. All right, so here we're going to talk about some trig identities now. First one we're talking about is the fundamental trig identity. I'll just explain where it comes from really quick. On the unit circle, if you remember, any point on the circle, call it P, has coordinates x and y. All right, and again, the angle that's formed is the angle with the x-axis. And again, remember that we also identified the point P with the sides of the triangle, and that was cos theta, sine theta. So the x-coordinate is cos theta, the y-coordinate is sine theta, and if it's the unit circle, the hypotenuse is 1. So the relationship in that triangle of the sides and the hypotenuse can be found through Pythagorean theorem, and if that's the case, it's sine squared theta plus cos squared theta equals 1. It's a squared plus b squared equals c squared. And that is the fundamental identity. So I'll just write it here. It's sine squared theta plus cos squared theta equals 1. All right? And then any rearrangement of the identity is also true. So for example, we can write sine squared theta is equal to 1 minus cos squared theta, or we can also write cos squared theta is equal to 1 minus sine squared theta. Again, the whole power of identities is anytime you see any one of these expressions, you can replace it with what it's equal to, because they're always true. Something that's worth noting here as well is the 1 minus cos squared or the 1 minus sine squared. Those are actually difference of squares if you think about it. So those could be factored. So you could factor this into 1 minus cos theta, 1 plus cos theta. Sometimes it helps to think in these terms. Because if you have just 1 plus sine theta or 1 minus sine theta, if you can, sometimes you might multiply by its conjugate, I guess, change the sign in between, and then you can make 1 minus cos squared theta or 1 minus sine squared theta, for example. The other important identity, we've already been talking about it, okay, we've already been using it, and that is tan theta is equal to sine theta over cos theta. And again, you can take that off the triangle that we drew up here. If you take opposite over hypotenuse, it's sine theta over cos theta. All right. The way that you would use identities maybe is in this case that we're going to show here. It's just in simplifying expressions. And when you simplify expressions, you try to reduce the number of trig functions. You might write with a common denominator. You might try and reduce it down to one term. All right. So for example here, this question here, we probably do this with it. So cos theta, we can't do anything with that. But tan we can change to sine theta over cos theta. And obviously, Everything else in the question's in terms of sine theta and cos theta, so it makes sense to change tan to its identity, sine theta over cos theta. So if we do a little step of work here, we get this. And now we have two terms. One's a fraction, one's not. It'd be good to add these together as fractions. So to do that, we need to write with the common denominator. So obviously the common denominator in the question is cos theta. So we'll just multiply this first term by cos theta over cos theta. And we end up with the common denominator, cos theta. And on top we have cos squared theta plus sine squared theta. And now here's the thing. Again, as soon as you see something that looks like identity, you can replace it with what it's equal to. And cos squared theta plus sine squared theta equals 1, right? So this can be reduced to 1 over cos theta. So we started with something fairly complex and we ended up with something fairly simple, 1 over cos theta. Again, these are all just equal to the first line. It's not an equation, okay? It's just a proof, all right? In the second question, again, we have two terms. We'd probably like to put them together as a fraction. So to do that, again, we need to write with a common denominator. To be able to do that, we'll multiply the first fraction by cos theta over cos theta, and we'll multiply the second fraction by 1 plus sine theta over 1. Again, as long as we're multiplying by the same thing, it's a quantity equal to 1, we can keep doing this. So on top, we're going to have cos squared theta, and it's going to be minus, and then again, here's what we talked about in the previous slide. We have 1 minus sine theta, 1 plus sine theta. Together those become 1 minus sine squared theta all over, and on the bottom we have 1 plus sine theta times cos theta. All right. In the numerator, we can, there's a couple ways we can go. You can either replace 1 minus sine squared theta with what it's equal to, what its identity is. All right. That's cos squared theta. So really this becomes, on top, cos squared theta minus cos squared theta all over 1 plus sine theta times cos theta. And obviously on top, cos squared theta minus cos squared theta becomes 0. So 0 over 1 plus sine theta cos theta. And that answer then is, final answer is 0. Okay. The other thing you could have done, if you would have expanded these or distributed the negative onto the brackets, you would have got maybe cos squared theta minus 1 plus sine squared theta. And again, over that same denominator, so 1 plus sine theta cos theta. Again, the interesting thing that happens here, obviously, cos squared, wherever you see a combination of cos squared theta plus sine squared theta, you can replace that with 1, and it would be 1 minus 1 in the numerator, which would also reduce to 0. All right? Good. Okay. Here's, again, a typical question that you might see. They tell you that the cosine theta, cos of theta is negative 3 over 5, and the angle is found between pi and 3 pi over 2. So again, the steps to solving this, first thing you're going to do, or you should do, is locate the angle. So if it's between pi and 3 pi over 2, we know it's in the third quadrant. So then we should draw that angle. Okay. And cosine ratio is adjacent over hypotenuse. So a couple things you have to know here is the hypotenuse is never negative. It's always positive. So the negative that's in front of the fraction will go into the numerator, and that'll become the adjacent side. Again, we're dealing with this angle in the third quadrant, but it's actually also the same as the full rotation angle, the positive rotation angle from 0. All right. And the question now says find sine and tan. Well, to find sine of theta, we need the side opposite. Okay, opposite theta. And obviously we don't have that, but we can find it. It's a right triangle, you know, two of the sides, so it's going to be negative 3 squared plus y squared equals 5 squared. And so we get y squared is equal to 25 minus 9, so it's 16. So y is equal to plus minus 4, if you're taking the square root correctly. But now you have to put it in the context of the question. Y represents a side of a triangle in third quadrant, so y must equal only negative 4. Okay? So you wouldn't even necessarily have to put the plus minus. Okay? You could just give the answer negative 4, give the appropriate answer. So, to answer question A now, sine theta is equal to opposite over hypotenuse. So that ratio is going to be negative 4 over 5. And then the tan ratio in part B is equal to opposite over adjacent. And so that is, it's negative 4 over negative 3, but obviously negative over negative is positive. And that obviously works out again with cast, right? An angle in third quadrant has a positive tan ratio, and that's how it worked out. Okay. You could also do the sine ratio over the cosine ratio. In this case, it would be a little bit more work, so you probably wouldn't do it that way. In the example at the bottom of this slide, again, it's another proof. It's showing that one side can be made into the other. And what we usually try and do is so for example, we'll call this the left side, this will be the right side. We try and make the left side equal the right side or vice versa. Usually start with the more complex and try and make it simpler. But in this case, the left-hand side has sines and coses in it. The right-hand side has tan and cotan. Just a quick note for those who weren't here, cotan theta is equal to 1 over tan theta. And so its identity can also be written as cos theta over sine theta, the reciprocal of tan. You don't need to know it, but it just comes up in this question. So what we would do in this case is we would try and simplify the right-hand side. So all you do is you work with the right-hand side. You don't cross the equal sign. All right, so we just go change this to sine theta over cos theta minus cos theta over sine theta. Obviously write with common denominator. So that, the first fraction we multiply by sine over sine, which would give us sine squared theta. The second fraction we multiply by cos over cos, which would give us cos squared theta, all over the common denominator of cos theta sine theta, which now you can start to see that it is exactly the same as the denominator on the left-hand side. So now all we have to do is work with the numerator. The numerator only has cos in it. So what we'll do is we'll use the identity for sine squared, right? Which is 1 minus cos squared theta minus cos squared theta all over, just change the order here, sine theta cos theta. And then on the top, it can be obviously 1 minus 2 cos squared theta over sine theta cos theta. All right. So again, what we've proven here now is we've proven that LS is equal to RS, and so we've proven the identity. Okay. This is not a typical IB question, but what it does is it forces you to use some of the identities. Okay. What we're moving into now are the double angle identities. So again, what you'll notice is it's sine of 2 theta, it's the cos of 2 theta, or sine of double theta, cos of double theta. And what they have is we have these identities that reduce the double angle to single angle. So over here you'll notice theta, and same thing over here. All these angles are just theta. So you'll see the purpose of this later on too as we work with equations. But sometimes in equations you'll have some angles will be given as 2 theta, some will be given as theta. What you need in an equation is you need all the angles to be the same. So what you would do is you would use the double angle identity, for example, then to write an equation in terms of just a single theta. All right. Notice that there's just one form of the sine of 2 theta. It's 2 sine theta cos theta. There's 3 forms of the cos of a double angle identity, but really the second 2 just come out of the first, and substituting in rearrangements of the fundamental identity in for cos squared or sine squared give you the bottom two, right? For cos squared, I can put 1 minus sine squared, and for sine squared, I can put 1 minus cos squared. And if you do those substitutions into the first form, you'll get the second two, all right? You can try that on your own, all right? Now what we'll do is we'll try a couple more examples, okay, with this. So here we go. So again, now we're given an angle sine theta is equal to 2/7, and we're told that it's between pi over 2 and pi. So again, what we need to do is we need to locate it, okay? It's going to be probably something like this, all right? So again, this is the angle theta, which is again the same as full rotation angle around to there. And again, sine is positive in the second quadrant, so, and then that's obvious. The y value is 2, the hypotenuse is 7. And we need to find sine 2 theta. The question's asking to give the answer for sine 2 theta. So again, what you'd probably do is write the identity for sine 2 theta. Sine 2 theta is 2 sine theta cos theta. So to be able to give the value of sine 2 theta, I need to know both sine theta and cos theta. Well, obviously sine theta is given. So I need to find cos theta. To find cos theta, obviously I need the adjacent side. So we need the x value here. So again, we use Pythagorean theorem, x squared plus 2 squared is equal to 7 squared. So x squared is equal to, it should be 49 minus 4, so 45. So x is equal to, it's going to be the negative root of 45, okay? So now we put those values into the identity. So sine theta, again, given, is 2/7. Cos theta from the picture is going to be negative root 45 over 7. And when we evaluate this, we get negative 4 root 45 over 49. And that's the exact value of sine of double theta without ever having to actually find theta. The B question asks us to find the cos of 2 theta. Now again, you have your three choices here. Anytime you see a double angle, you should be thinking identity, replace with identity. For cos 2 theta, you have three choices. I would use the one that only uses the given information from the question. So for example, I would use the one that were in the form 1 minus 2 sine squared theta, because sine is given. Just in case you made a mistake earlier. So the sine ratio, we said, was 2/7 squared. So this is 1 minus, that's 2 times 4 over 49. So 2 times 4 is 8 over 49. And 1 is 49 over 49. So 49 over 49 minus 8 over 49 makes 41 over 49. And again, that's the cos of double theta. Okay, so again, our theta that we're talking about is the full rotation angle from 0 to that location. And if we doubled that angle, this would be the cosine ratio, or that would be the sine ratio of double that angle. Again, all of those done without ever having to actually find the angle. In C, we want the tan of 2 theta. Well, tan of 2 theta is actually, the identity can be extended to different angles. So the tan of 2 theta, the identity for that is sine 2 theta over cos 2 theta. So now we can use the two ratios we found in the two other parts. So negative 4 root 45 over 49 and 41 over 49. When you divide these two fractions, obviously, when you divide fractions, you multiply by the reciprocal. You can try this on your own, but you'll notice that the two denominators that are common, the 49s, will cancel out, and it ends up being the top numerator over the numerator in the top fraction over the numerator in the bottom fraction. So this answer should be negative 4 root 45 over 41. Okay. All right. We'll skip the bottom question. A couple other proofs here that you can play around with. Again, when you're doing these proofs, you're just trying to prove that the left-hand side equals the right-hand side. The character, the Greek letter that's being used doesn't matter either, obviously, I think. Sine 2 alpha, tan alpha, cos 2 alpha. On the second half of the slide, it's a phi or phi, sine 2 phi plus sine phi, cos 2 phi plus cos phi plus 1. All right. Again, the big thing you're going to do here is you're going to write with the identity. All right, so, or replace with an identity. So sine 2 theta, I'm going to replace that with 2 sine theta cos theta, and then I'm going to replace tan. Tan you almost always want to replace with sine theta over cos theta. And then the cos 2 theta, what we can do is we can just take a look here. Let's see what's happening with the first part of this side here. So you notice the cos thetas will cancel. We're going to have sine squared theta. So I'm going to use the form of the identity that has only sine squared. So I'm going to use 1 minus 2 sine squared theta. Okay, and again what we're doing is we're only working on the left side. I'm not working across the equal sign or anything like that. I'm trying to make the left side into the right side. So this is now 2 sine squared theta plus 1 minus 2 sine squared theta. Obviously the 2 sine squared thetas cancel and we're left with 1. And again what we found is that left side equals right side. All right. Okay, so we're running short on time. I'll let you do the other proof on your own. Just a couple of questions here at the end. This is ultimately what we're working towards. We're solving equations, all right? So we want to find all the values of x where sine 2x equals cos x on the domain from 0 to 2 pi. So again, and this is where this comes up in equations, is we have a mix of angles. You don't like that. Generally, we don't like a mix of trig functions either. So you try to get it all in the same trig function, usually sine or cos, and you always want it in the same angle. So in this case, we have 2x and we have x. So that's not good. So that's why we use the identity. So we're going to have the first line of our equation. Now this is an equation, so now we are working across the equal sign. So 2 sine x cos x equals cos x. We're finding answers for x. Okay. Now here's the thing, really important with this one. Everybody always, when they see this, are tempted to divide cos x off of both sides. Do not do that. All right. I'll make the note here. I did it in class as well. Never divide out a trig function. If you do that, you lose solutions. You lose points on your answer. Never divide out a trig function. Very, very important. Okay. So what we're going to do here now is we're going to have to bring the cos x all to one side. Very often this is the solving procedure. As you bring all your terms to one side, it might end up being some kind of factoring that you can do. All right. So we have, it's going to be 2 sine x cos x minus cos x is going to equal 0. And again, this is that same as quadratic factoring. Look for either common or some type of quadratic factoring. In this case, it's just going to be common factoring. So we take out the cos, and we're left with 2 sine x minus 1, all equals 0. And now, again, same as quadratic factoring, set the factors equal to 0. Okay, so the left column here is done. If we rearrange this one on the right, we get sine x equals a half. And now what we have to do is, we've already been doing this. Like I said before, this is the last step of your of solving a equation generally. So anytime your value cos or sine is equal to 0, 1, negative 1, I would just use the unit circle. Okay. So again, you may not have to draw it every time, but that's right. I did it the wrong way. This is 1, 0. This is 0, 1. This is negative 1, 0, and this is 0, negative 1. So again, we're looking for all the places where cos is 0. Cos corresponds to the x coordinate. So our answers here for x are pi over 2 and 3 pi over 2. Okay. For the other one, sine x equals a half. Okay. Now again, you have to use your knowledge of, first of all, you want to know which angle has a sine ratio of 1/2. If you look in your table, you'll see that it's pi over 6. We need to work in radians. And where is sine positive? Well, it's positive in the first quadrant and the second quadrant. So in both of those quadrants, there will be a pi over 6 reference angle. So the two answers for this are x is equal to, that's pi over 6, or in the second quadrant, that angle, 5 pi over 6. And again, we're only allowed to go between 0 to 2 pi. So these would be the 4 answers. Right? You have 4 answers in this case. X equals pi over 2, 3 pi over 2, pi over 6, or 5 pi over 6. All right? And then just one more example I just want to do with you, just because it kind of goes against what we just looked at. If your question was this, sine x equals cos x, okay? On the last slide, I said never divide out a trig function. I'm actually going to tell you, in this case, this is the only case where you are allowed to divide by a trig function, but you're actually not dividing it out. So what we're going to do is we're going to divide by cos x on both sides, all right? But the thing that happens here is that sine x over cos x is an identity, and that's tan x. So the cos is not really gone, it's still inside the tan, and cos x over cos x is 1. And so now what we're doing is we're just solving the equation tan x equals 1. So again, look in your table, which angle has a tan ratio of 1? Well, it's 45 or pi over 4. And where's tan positive? Well, it's positive in first and third. So it's going to make a pi over 4 reference angle in both of those quadrants. Okay? And again, if the domain was 0 to 2 pi, let's say, it could be 0 to 360 or whatever. The answers for x are going to be, again, like we said, pi over 4, but then also the positive rotation angle around to the second location, which is going to be 5 pi over 4. So in that case, you have the 2 solutions again. Again, just wanted to emphasize that this is the only case where it's okay to divide by a trig ratio, but it's because it still exists. It's just in another form. It's in the tan function in this case. All right. So do the exercises for this and get some practice, and then be ready to ask questions in class.